Alright, so it's the first hard level question on my channel, 297, serialize and deserialize binary tree. So it's a relatively easy one among the hard level questions. This question asks us to design an algorithm to serialize and deserialize a binary tree. The serialization is the process of converting an in-memory object into a sequence of bytes, so that you can either dump it to disk or you can transmit it through a network. And deserialization is the process of taking that sequence of bits and reconstruct the in-memory objects. So this question asking us to turn a binary tree, which is given by the root node, into a sequence of bits, and the deserialize method is going to take that, take the output from serialize and return a root node to the newly constructed binary tree. So that's pretty much what the question is asking. There is no specification on how the serialized result should look like. There is no specification on which method you should do to perform this serialization and deserialization. But you can imagine that they would just among 4 different choices, I guess. Potentially 4 different choices: level-wise traversal, in order, post-order, or pre-order. With the first one be breadth-first search, BFS. The latter 3 will be depth-first search. So I'm gonna code a solution with the pre-order, depth-first search, and I'm gonna solve that in 2 levels. One is the with the sequence bits to be in ASCII characters. So that you can imagine it would be similar to something like a JSON or XML. It's targeted as easy to parse and also human readable. The second solution I'm going to have is going to be the same pre-order traversal DFS version of the algorithm, but it will be in the binary kind of sequence of binaries. So it will be more memory compact, but not really human readable. So the trade-off it's between these 2 solutions is really in the if you want a more compact, smaller file size, you would go with the binary. If you wanted to have some kind of a human readable, like this one here, you would go with the strings. So this question, based on the signature here, or it's suggesting us we should return string, but since Python is not really typed, so we could both 2 should be okay with the Leetcode judging test system, I guess. So yeah, so just quickly on the quickly on the pre-order traversal, like this tree. We're gonna end up with something like, if we use what the Leetcode is using here, it would be like 1. We visit the node itself first, then to its children, and for the children we go with its 2 children. No. Then we backtrack to the right children, which is 3 here. Then we go to 4, and no, go back to 5, and no. So this is the full representation in pre-order traversal. I guess we could do some trims to get rid of the null and nulls. That's some kind of optimization we could do. Just imagine if you have a full tree, and if you just record all the nulls, it will be double the size to the maximum. So because it's binary tree, it's going to be double in the worst case. So it's still linear in terms of number of actual nodes in there. So not too bad. So I'm not going to do optimization on that around that kind of area. I'm going to just code the string ASCII string as the serialization, and later on a binary. So that's pretty much it. I'm gonna start code. It's already very late. Hope I can finish quickly. Alright, so let's get into the code. So basically what here we should return a string which we will separate the node values or the nulls by comma, just following what Leetcode is doing. So we should return something like here. So initialize this to be empty array, and we have a encode method which takes a node and just do BFS. So it's going to be a recursive version. You can improve it to iterative version. It's not too difficult. Let's stick with what they have. So if it's null, we return a representation for null. Otherwise, we return a string representation of the integer value. So that's for the node itself. Then we recursively do this for two children. So encode node.left. And we just need to call this on the root node, and that's pretty much the serialization code. We can swap this to like a string stream, so that just keep piping stuff into it. But for the ease of coding, we're just gonna use an array to append stuff to it. So that's pretty much for the serialization part. Then it's the deserialization. We're basically gonna split the input string by the comma, and recursively doing DFS search to reconstruct the whole tree. So we're gonna use a DAG so that we can pop the leftmost item at a lower cost. Let's write the decode method, which should have no argument. We just work on the DAGs here. Let's actually just call it DAG. So we will pop for each iteration. We're gonna pop the leftmost item from the DAG, and we're just gonna recursively call that twice, and assign each to the left and the other one to the right. If it's null, we return the null pointer. Otherwise, we will actually construct a node in memory. It's called tree node. Let's convert the node's value into integers. Right? It's an integer. It doesn't really say. Yeah, let's actually do this. And we should return the node in the end. The root for the reconstructed node will be just calling this method, and we should return that. So that's pretty much the decode method, which is quite aligned with what we have here. We handle the null first, then a node, then left, right. Here it's null, node, left and right, exactly matching the sequence. So we have 4 lines here and 4 lines here, 5 lines, you know, with 1 extra popping from the deck. So that's pretty much it. Let me try to run it. I'm not sure if it works. Okay. What's the problem? Okay, there's missing dot there. Right, let's see. Yeah, it's working, so quite fast. I'm not sure about the memory thing here. Yeah, so that's the string kind of formats. Let's talk about binary formats. So yeah, I'm gonna comment this and start code the binary format. We're gonna have a byte string which initially is empty. We're gonna keep piping new binary stuff into it. So for every node, we're gonna use something like you know, since this is basically a design algorithm for the binary, you know, like a HTTP header or the stuff like protocol buffer or what's that thing called, thrift. Usually it's they have a design, you know, the maximum length of how much, and for a certain number of bits it's either a flag, and a certain number of bits it's actually the data. This is gonna follow that same format. We're gonna use 1 bit for one byte for flag, indicating the situation of this current node, whether it's null pointer, or it's a single node, or it's a node with either left or right. 1 byte is going to be enough for that type of node, and we're going to use 4 byte for the node value. The reason being that the previous example, I guess the values are, I think it's integer, because I convert that into integer, pass all the test cases. And for most other languages, usually default int is like 4 bytes, 34 bits, 32 bits. So I'm gonna use that. So the binary representation is gonna be something like 1 byte flag and 4 byte data. It's gonna be a sequence of this thing, and just you know, stitching together, one for instead of the you know, the string representation for value or null. It's gonna be a sequence of bytes. So the reason why this 1 byte is gonna be enough, it's actually 4 bytes is enough, I think. 4 bits is gonna be enough. We're gonna use 0 as indicating that it's a null pointer, and we're gonna use 1 to indicate it's a isolated node, and oh no, not really. We're gonna use the first bit. If it's a 0, if the first bit is 0, it's a null. If the first bit is 1, indicating there is indeed a valid node in there. We're gonna use the second bit, you know, towards the second bit to indicate it has left children, and we're gonna use the third bit to indicate it is it has a right children. So yeah, let's put it here. Has left. The third bit is 4, so it's So let's imagine we have something like 1 1 and 1 1 1. So this translates to b of this. I think so. It's 0x. No. So if we have a binary representation, I forgot the prefix to this. But just imagine it's a binary representation for the number. If it's a 1 1 1, it means that it has right, it has left, and it's a valid node. Node with 2 children. And 0 0 0 means node, not pointer. 0 0 1, it's node with no children. And something like 101 is node with only right. So this is the flags basically, and you can figure out the node with only left children what that looks like. So I'm gonna write this thing here. We're gonna have the SAM encode method, which takes in a node here. Just align that because the algorithm part is still the SAM pre-order depth first search. We're gonna use a helper function to create this flags. So that's what here says. It's 3 bits to indicate what kind of situation this node is. And we're gonna write that to the IO string, to the byte string, which is the flag to 2 bytes, and it's 1 byte. Just gonna use a little. So if it's null, we're gonna return. Otherwise, we will also pipe in the value for the node. So that will be the node value is the integer. We're gonna use 4 bytes, and it could potentially have negative numbers. So we're gonna use signed number. And we're gonna do this recursively on both left and right. And we're gonna after the byte string is formulated, we're gonna go back to the beginning and just return that whole byte string as the serialization. So that's go back to the beginning. We read out the whole byte string and return that. So then it's define this encode flag function. So it's gonna be static. Okay. Node. We're gonna start with 0 here, and just based on the different situation this node is, we're gonna flip the bits by doing OR operation. Turn on the bits by doing OR operation. So if it's a valid node, we turn on the refresh the bits. Otherwise we do nothing, or we just return 0 0 0. Node.left, we turn on the second bit. if it has a right children, child, I would turn on the third bit. So that's pretty much the flag. With this flag, we encode the node as 1 byte for the flag and 4 byte for the node value, integer value, and it's assigned integer. We use recursion to do the same thing on the left and right children. So it's quite similar to it's exactly the same pre-order DFS algorithm, just to encode that into lower level representations. Then we write this. We implement this Deserialize method, where this data now it's a byte string. So we first create a buffer for that. Byte.io the data, and then is the decode method. We're gonna grab the flag first, which is gonna be the very first byte. It's gonna be int from bytes. Okay, so it's the byte first. We read 1 byte, and this is the order. So just matching exactly this, we get 1 byte in little, and this is when we write the flag, it's a 1 byte in little. So that's a correspondent that match exactly, so we can recover the flag perfectly. And so this is determine whether this whether this node it's a null or not. So the only situation when this whole thing will return true is that we are in I guess this situation, right? Yeah. The only situation when we're gonna have that have this to be true is with the very last bit of flag to be 0. So we do a negate. We will turn that 0 to be 1, and 1 and 1 will cause us to return 1. Yes, 1 and 1 will be 1. Other cases, in all the other situations, I'm gonna actually write out all that's just write out all the possibility for the flags. I should do that in the very beginning. So in all the situations except for the null case, the last bit is 1. So when you're using negate to flip that, you get 0. That's all 4 other cases are 0. So 0 and 1 you will get 0. The only case this will be true is the node is null. This corresponds to this case, except in the higher level representation, it's an actual string of null. Otherwise, in here it's the flag. And then we will grab the node's value and use that node value to construct this tree node. The hint is really useful and we have to use assigned number. Then we recursively use this decode method on both left and right. And we only do that when we know that we have left children. So there will be some condition in here. So this is basically check whether we have we do a negate, then use an AND operator. It's basically check whether that particular bit it's a 0. So yeah. So when we check whether the second bit it's a 0, it's checking whether we have a left child or not. So that's what this condition here says. So if we don't have left child, we set that to none. Otherwise, we will recursively call decode to actually create another tree node and establish the reference. So yeah, that's for the right child. Okay. Then this is pretty much the same, right? Yep. So I can actually comment this out. Cool. Yeah. So let's actually make this two things more aligned. So. Okay. So if we comment this out and uncomment the above, we switch back to the string representation. Otherwise, this current version will be the bytes version. And it's the same for this deserialize code. Let me quickly check if I got problems. So it looks okay to me. Let's try submit this. Okay, it's working as well, about the same speed. So yeah, here you have it. In terms of the memory used, they are actually similar to the previous version, but the serialized string, the sequence of bits, it's gonna be smaller in the byte formats. So especially when you have large integer for the values here. Yeah, that's it. That's this question 297, serialized and deserialized binary trees.